Hello everybody and welcome you all to the sixth session on network theorems, in which we are looking at the Millmans theorem. Before this, dear students, we have seen 5 theorems, and this being the sixth theorem, that is Millmans theorem, and let's look at the statement of the theorem. If n generators of EMFs E1, E2 up to En with internal impedances Z1, Z2 up to Zn are connected in parallel, then the EMFs and the impedances can be combined to give a single EMF E with internal impedance Z, where E is given by this equation and Z is given by this equation. The student, try understand that here we are considering the n generators. You can consider them as the voltage sources, okay, of EMFs V1, E2 up to En, and they are saying that they are coming with the internal impedances Z1, Z2 up to Zn, and they are all connected in parallel. If such parallel combination of the n generators are there, then that can be replaced by single EMF E with internal impedance Z, where E and Z are given by these equations. So this is what Millmans theorem is all about. Now we shall see how to derive these equations. Fine. So provided E1 Y1, E2 Y2, En Yn are all given, how to obtain E? Fine. How to obtain Z? Yes, they say that from these two equations we can obtain E and Z, but how to obtain these equations? How E is this and how Z is this is what we are interested in looking at. Okay, so let's get into that. So this is what is the circuit that the Millmans theorem is talking about. Can you make out what type of circuit is this, or the network? I've told you circuit and network can be interchangeably used. They are the terminologies which can be used interchangeably, but to be precise, since there are the open circuit terminals, we can call them as network. Fine. So across two open circuit terminals you have these parallel combinations. Fine. What type of network is this if you have this open circuit terminal? So what is this? This is linear circuit. Mind you, in all the theorems that we have seen so far, we are using linear circuits only, and along with that, being linear, it is also two terminal. That means it's a linear two terminal network. In a linear two terminal network, if you have the EMFs E1 in series with Z1, EMF E2 in series with impedance Z2, okay, and such branches connected in parallel like this in your linear network, then such a network can be replaced by an equivalent one EMF in series with one impedance Z. So how to obtain Z and E now is what we are interested in. See here, across these two terminals they have marked the voltage or the EMF E. Fine. Now we are interested in looking at how the equation for E can be obtained. How can we express E in terms of these EMFs and impedance? Fine. Now let's approach this problem using node analysis. Okay. So in node analysis, what is that we have to look at? We have to look at the number of nodes, and after we get to know how many number of nodes are there, we mark the node voltages. So here also we need to do the same. So can you make out how many nodes are here? How many branches are there? There are n number of branches starting from 1 up to n. So they have generalized it to n branch problem. Fine. Now how many node network is this? See what's happening. There are all the branches are connected in parallel. They are all connected in parallel means what? Each branch is coming and getting connected at one node. So that means there is just one node to deal with. Okay. Now one node will have one node voltage marked. So what is the node voltage here? See here, if you have a voltage across these 2 points, okay, what does that mean? You have a voltage here across these 2 points. That means between this and ground is where E is dropping. Ground we have not marked, but the meaning is E is dropping across this terminal and the ground terminal. Fine. If it is so, we can say that the node voltage at this point is actually E. Fine. Now, if we know the node voltage here, it would be easier for us to write the equations for current in these branches. Okay. Another thing that node analysis deals with is, after we mark the node voltages, we need to look at the currents. Okay. Let there be any number of branches, we need to have the currents in those branches. Fine. And after that, there would be some currents entering the node and there will be some currents leaving the node. Okay. What does KCL tells you? KCL tells that the sum of the currents entering should be equal to the sum of the currents leaving. And one more assumption that we made when we are dealing with node analysis is that unless there is a current source which shows the current to be entering the node, we consider all currents to be leaving currents. Fine. Now see, in these branches, do we have any current source which is showing the current entering the node? No. We only have the voltage sources along with these internal impedances, no current source present which is showing the current entering the node. That means no entering current is present there. So that means all the currents that we have here in n number of branches are all the leaving currents. Fine. So how would the KCL looks like in this case? In this case, the KCL can be written as the sum of the currents leaving the node is 0. So that is what we are going to do now. And one more thing is, see here in this arrangement, we have shown the Z1, Z2, Zn externally, but they are not the external impedances connected in series with these EMFs. No, they actually are the internal impedances. They are the internal impedances which are existing along with these sources. Fine. Now, keeping that in mind, we shall go with applying the KCL. Now, what is the voltage? We have the old node here. Okay, let's call this as node E. At node E, what do we have? The voltage. Okay, the voltage is V or the EMF is E. Now, KCL at that node, KCL at this particular node gives you what? Now, that is the currents, the sum of the currents leaving is what we need to obtain now. So, how to obtain the currents leaving this node? So, they are all the same nodes. See, we have these points, right? They are all the same points because they are connected by short circuit. Fine. So, what is the current in this particular branch? It is E minus E1 by Z1 is the current that is flowing in this branch. What is the current that is flowing in this branch leaving this node? That is E minus E2 divided by Z2. Similarly, we have n such currents leaving this node. Fine. So, you have to take the sum of all those leaving currents and we would get that equal to 0 since there are no currents entering. So, this is what it looks like. Understand? So, this is what are the currents that we just saw. There are n branches have n currents, all the currents are leaving. So, sum of these currents leaving should be equal to 0. Get this point? Now, we shall deal with this equation to obtain the equation for E. That means we are trying to obtain the equation for E in terms of the other impedances and the EMFs. Fine. So, how to do that? Consider this. Now, see what's happening. In this equation, we have terms E by Z1, E by Z2 up to E by Zn. So, in that, if you take common, you will be left with 1 by Z1 plus 1 by Z2 up to 1 by Zn. So, group them together taking E as a constant in these terms. Fine. And what is remaining there? Minus E1 by Z1, minus E2 by Z2 and minus En by Zn are remaining. Take them onto the right hand side. Fine. So, now what we can do here, what is Z? Z is the impedance. What is inverse of that? Inverse of that is the admittance. How do we denote admittance? If Z is the impedance, admittance is denoted by Y. And that is what we are going to do now. We will be expressing all these impedances in terms of the admittances, and when we do that, the equation actually looks like this. See here, 1 by Z1 is Y1, 1 by Z2 is Y2. Similarly, all these impedances are expressed as the admittances. Now, what is that we are interested in? We are interested in obtaining the equation for E. So, what you would do from here on? So, you would be writing the equation for E means this particular term would come to the denominator on the right hand side, and that is what we have given here. So, this is one EMF that we have obtained from the EMFs and the impedances that were connected in parallel. Fine. Now, we also have to obtain the equation for one impedance which is there as the internal impedance with one generator that we have obtained. Fine. So, how to obtain the equation for that? See here, since I have told you all these are internal impedances. If you cannot catch that point, you cannot say these are all in parallel. Since they are all internal impedances, we can say that Z1, Z2 up to Zn, all these impedances are connected in parallel. Okay. Since they are connected in parallel, how can we write the equivalent impedance across these two terminals? How to do that? See here, since all the internal impedances are in parallel, we can write 1 by Z, that is Z is the equivalent impedance, okay, and that is equal to 1 by Z1 plus 1 by Z2 up to 1 by Zn. Now, I have told you what is 1 by Z. 1 by Z is Y, and 1 by Z1, 1 by Z2, you can represent that by Y1, Y2 up to Yn, and that is what is being done. But we are interested in Z. So, what can we do? So, if you write it as 1 by Z, okay, and this you keep as it is, you will find your Z to be like this. So, we have obtained the equation for E and Z. Fine. So, this is what Millmans theorem was talking about. If you have such an arrangement of branches connected in parallel, all these impedances and EMFs can be combined to get one EMF in series with one impedance, that is one generator equivalent. Okay. So, this is how we derived the equation for the EMF and the impedance. Now, with that, we shall directly try solving the problems. Now, in problem number 1, they are asking us find the current through 10 ohms by Millmans theorem. See here, there is a 10 ohm here, and through 10 ohms I is flowing. So, where did you find such a question? In which theorem have you seen such a question wherein you were asked to find out the voltage or I by using some theorem? Try recalling. The first two theorems, the Norton's theorem and the Thevenin's theorem. What were we doing? We were solving two types of problems there. If the two terminals open circuit is there, you can find out the Thevenin's and Norton's equivalent across those terminals. And what was type 2 problem there? Finding V or I in any part of the circuit by using the Thevenin's or Norton's theorem. Okay. So, it is similar to that. So, that means they have asked us to find out I by Millmans theorem instead of the Thevenin's and Norton's. So, what we used to do in Thevenin's and Norton's when we were finding out the voltage and current needs to be done here also. What is that? If you remember, try recalling what we used to do there. We used to disconnect the branch through which the current or the voltage was present. Okay. So, after disconnecting, what happens? We avail the two terminals, the open circuit terminals. So, across those two open circuit terminals, we need to obtain what is the equivalent circuit or the network. So, that is what we shall try doing here also. So, in the solution, the very first step deals with disconnecting this. Fine. So, that is what we will be doing. Remove 10 ohms and mark terminals AB. So, why I am marking that as AB? So, it would be easier for us to refer to those terminals. Every time you can say open circuit terminals, or to be precise, you can say across the open circuit terminals AB. That is why soon after you avail those terminals, name them so that we can refer to them easily. Fine. So, what is that we need to be doing? we now need to obtain one EMF, one resistor equivalent across these two terminals. Okay, and these two terminals can be brought here. Fine. So that is what we do here. Now, so you can see these terminals here. Now, what is Millmans theorem? If you have the branches which consist of the voltages and resistances like this, if you have such branches connected in parallel, then that can be replaced by one EMF and one impedance equivalent network like this. So that means now we have to obtain E in terms of these Z's and E's, and Z also in terms of these impedances. So how to do that? So we have just derived an equation, right? So using those equations, we need to obtain the value of E and value of Z. Fine. So let's try do that now. Now the equation is this. So when we derived the equation, remember we had n number of branches. Fine. So after this point we used to give dot 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 dot. That means starting from branch 1, branch 2 up to branch n. Now this problem is just 3 branch problem. So that's why we are limiting this particular equation to 3 EMFs and 3 admittances. Get that point? Now among these impedances and EMFs, we have to identify E1, E2, E3 and Y1, Y2, Y3. Okay. Now see here, this is our E1, E2 and this is E3. Now how E1, E2 is different from E3, can you make out? What is differing? This is fine, but here something is different. What is that? It's the polarity. So in a hurry, there are chances that we may not see this carefully. Okay, so we may miss on that. So you need to be really careful regarding the polarities of the EMFs that they have given there. Fine. So in that sense, if E1 is 22 and E2 is 48, E3 has to be minus 12, mind you. It is minus 12, not plus 12, because of the opposite polarities given here. Okay, and this is impedance 5 ohms, impedance 12 ohms and impedance, sorry, they are all resistances. Since we have written the equation in terms of the impedance, let's refer to them as so. But they are all the resistances. In place of Z1 you will have 5 ohms, Z2 12 ohms and Z3 4 ohms. Fine. But what are here? There are Y's. There are no Z's here. That means we have written the equation in terms of the admittance, not the impedance. This is another thing that you need to consider. You just cannot take this 5 and substitute in place of Y1. No. What is Y1? Y1 is 1 by Z1. So this is Z1. So Y1 needs to be substituted as 1 by Z1. Get that point? Now with those substitutions, your equation would look like this. And another thing that I would like to advise you is that you have to substitute and then calculate. There are students who straight away go for calculations and will do mistakes here and there in a hurry. Okay, the time permits, don't worry, you will not be falling short of time. Substitute and then do the calculations, because you will have such cases wherein the EMFs could be of opposite polarity. That's why substitute the values and then go for calculations, and when you calculate E, that E happens to be 10.125 volts. Get this point? Now E is 10.125, that is something that we have obtained from this particular equation. Okay, now we need to obtain Z also. Fine. So let's see the equation for Z. The equation for Z is this. What is that? Z is equal to 1 by Y1 plus Y2 plus Y3, and substitute the admittances there. We are given the impedances, but we are substituting the admittances. That's why you have to substitute it as 1 by 5, 1 by 12 and 1 by 4 mohs. Okay, so this gives us 1.875. So what is that we have done? We have obtained the value of E and value of Z. Okay, so that means what is that we have done by Millmans theorem? is this. We had 3 branches with some EMFs and some impedances. So we have combined them to obtain one EMF in series with one resistance like this. So this is what Millmans theorem is. But problem does not end here. What is that they have asked? They have asked us to find out the current through 10 ohm resistance. What did we do with that 10 ohms in step 1? We disconnected it, and whatever we have done across those 2 terminals. So across those 2 terminals we have obtained this. So now to find out that current I, we need to reconnect that 10 ohms. So to find I through 10 ohms, what is that you need to do? You need to connect 10 ohms across terminals AB, and when you do that, it looks like this. Fine. So these are something that we have obtained by Millmans theorem, and once you have this, bring this 10 ohms back so that you have a complete circuit. Fine. And the I starts flowing here. Fine. And to find out I, what would you do? KCL or KVL. So since we are talking about a closed path, okay, so we go with KVL, and that KVL looks like this. Why is this minus? Why is this minus given there? Because which direction we are moving? We always move along the clockwise direction, and when we are moving along the clockwise direction, we come across the negative sign. So that's why we have considered minus, and the other voltages are this resistance into I1 and this resistance into I. It's not I1, it's I. Okay, so this into I, this into I. So if you sum them up, if you add them algebraically, it should give us 0. That is what Kirchhoff's voltage law says. Now you have one equation, one unknown, you can easily find out the value of I. So this is what is the current that is flowing through 10 ohms. So this is what we need to do if they ask us to find the current through any of the resistors. Disconnect that, okay, get your network equivalent to one EMF in series with one resistance or impedance, and reconnect it to find out what is asked. So this is what we have done. So let's get into problem number 2 now. Okay, now see, in problem number 2 they are asking us to find out R such that the maximum power is delivered to the load is 3 milliwatts. So suddenly what's happening? Maximum power transfer. So we start wondering why they have to ask us maximum power transfer here. See, look at this. This is something that is very interesting. What they are asking? They are asking us to find out the value of R, which gives us the maximum power 3 milliwatts being delivered to the load RL. Fine. Now you do not have to bother. Just see these branches. How these branches are? You have voltage in series with resistor, voltage in series with resistor, and such 3 branches are coming in parallel, and that is what we need to deal with the Millmans theorem. Millmans theorem demands that. Okay, now let's not bother about this RL as of now. Let's keep this aside and just deal with this part of the circuit. Fine, and soon after you take this off, what would be available to us? We'll be availing 2 open circuit terminals, and let's name those open circuit terminals as AB. So now what is possible to be done here? What you can do? Let's not bother. They are asking us to find out the condition for maximum power transfer. Let's not bother about that. As of now, let's only think what equivalent we can obtain across AB by Millmans theorem. Fine. So what can we do? We know we have 3 resistors and 3 voltages. Use the equation for E and Z to obtain 1 R and 1 voltage. Okay, so let's try do that now. Using Millmans theorem to obtain one generator of EMF E and internal impedance Z across AB. So this is what we need to do. This is what we have, and this is what we need to obtain. Okay. Now, again, this is a 3-branch network, so we have limited this particular equation to 3 EMFs and 3 admittances, go on substituting the values. Okay, what was the resistance of each branch here? It's R. Okay, so since we are dealing with Y, we take the inverse of that and substitute them as 1 by R, and that the same thing is happening in denominator also. So what you can see, if you operate on this, you will find that actually you are getting your E to be 2 volts. So this is the value of E that we are obtaining. Fine. Now let's see what value of Z we can have with this equation. Z is given by 1 by y1 plus y2 plus y3. y1, y2, y3 all are 1 by R. Okay, and if you substitute them as 1 by R, you will find the impedance equal to R by 3 ohms. Okay, what is the impedance that we are getting? We are getting that to be R by 3 ohms. Mind you, that means we have obtained one voltage and one impedance, and that is what is Millmans theorem is all about. Okay, so Z is R by 3, and so what we have obtained is this. From Millmans theorem, we have got one voltage and one resistor equivalent network. So have you seen this one voltage in series with one resistor anywhere in any of the theorems? Yes. Where? In Thevenin's theorem. Exactly. In Thevenin's theorem, we have 2 volts in series with the resistor. Okay, so that means by Millmans theorem, what equivalent circuit that you are obtaining, that actually is the Thevenin's equivalent network. So that means this Z, what you call in Millmans, you can call that as ZT in Thevenin's. E, what you are calling in Millmans, can be called as VT, the Thevenin's voltage in Thevenin's equivalent network. So it is just the differences in the theorems. That's why the notations differ. Okay, so that's why we can call this R by 3 as RT and this 2 volts as VT. This is what we do in Millmans. This is what we do in Thevenin's. That means the Thevenin's impedance is actually the equivalent impedance that you obtain in Millmans, and EMF that you are talking about is actually the Thevenin's voltage. Fine. So this is what is the conclusion that we can draw. This is one information that we can extract from this. Now, can you make out why the question is talking about the maximum power transfer? Okay, so that means if we have to obtain the maximum condition for maximum power transfer, what we used to do, we need to first see which type of circuit we are dealing with. Are we dealing with AC circuits or DC circuits? In AC circuits, you can connect two types of loads. One is ZL, that is the impedance, and another one is RL, that is purely resistive load. Okay, in AC circuits, what impedance you will connect for maximum power to be transferred? You will connect the impedance ZL equal to complex conjugate of the ZT, that means the Thevenin's impedance. Fine. If you are dealing with the purely resistive load in AC circuits, then that resistive load should be equal to the magnitude of the Thevenin's impedance. Fine, but the circuit that we are dealing with here is DC circuit. So what is the condition for maximum power transfer in DC circuits? So that means the load that you connect here, the RL that you connect here, need to be equal to RT for maximum power to be transferred to the load. Okay, so that is what is the information that we need to have with us to solve this problem. So what we're doing, therefore by maximum power transfer theorem, for maximum power to be transferred to the load in DC circuits has to be equal to RT. So that means the load resistance RL has to be equal to RT for maximum power to be transferred to the load in DC circuits. So that is what we'll be doing here. You have VT, you have RT with you. Okay, what RL you need to connect? You need to connect your RL as RT. So this is what we'll be doing here. See, we have obtained this as R by 3, we have obtained this as 2 volts, and the same R by 3 you will connect across the load because I want the maximum power to be transferred to the load. But in this problem, what's happening? They already have given us what is the maximum power that is being transferred. And for that maximum power to be transferred to the load, what R needs to be connected in the circuit is what is the question. So how do we deal with? Let's obtain I first, okay, by applying the KVL. See, we are moving in clockwise. It's minus 2 plus r by 3i plus r by 3i equal to 0. So this is what the KVL is all about. Now, after that, we can obtain equation, the value of I in terms of R. So I is 3 by R. Now let's deal with the power. They already have given us the power 3 milliwatts. So if the maximum power 3 milliwatts has to be transferred, what should be your R which is there in the circuit given is the question. So let's do this to deal with this problem. So you all know the maximum power can be dealt with as I squared RL. Since this is DC circuits, we just have I. Otherwise, what we should have done in AC circuits, what do? We consider the magnitude of I. Okay, we consider the magnitude of I and then square. But in DC circuits, it's I squared. Whatever we can, that would suffice. Understand? Now, I is 3 by 3 square of that into RL is R by 3, and you know what your P max is, that's 3 milli, and if you work, you will get your R to be 1 kilo ohm. So what is the conclusion that we can draw from this? We can say that if you connect resistance R equal to 1 kilo ohm, then the maximum power of 3 milliwatts would flow to load. Okay, so this is how we need to solve this problem. Fine. Now, that is what this statement is saying. Therefore, 1 kilo ohm resistor has to be connected as the load resistor for maximum power of 3 milliwatts to be delivered to the load. So that this conclusion, every time you solve a problem, just don't leave it to the values that we are finding out. Okay, try concluding it, okay, with the statements like this, so that it would be clearer when you are examined. Fine. Now let's look at the summary of what we have done today. For Millmans theorem to be applicable, the network has to contain multiple generators connected in parallel. So then only you can think of Millmans theorem. Fine. One generator equivalent of EMF E and internal impedance Z obtained from multiple generators connected in parallel is a Thevenin's equivalent. That means from this type of arrangement, from the parallel parallel branch arrangements, what you obtain, one EMF and one impedance equivalent, that actually is the Thevenin's equivalent circuit. And what is the third point that we can understand? Millmans theorem, Thevenin's theorem and maximum power transfer theorem are interlinked. Why this statement? We have seen in the previous problem. What did we see? We saw that we thought we shall take Millmans and we obtained the Millmans equivalent. Millmans equivalent across the open circuit terminals is actually the Thevenin's equivalent. Okay, and when you have Thevenin's equivalent, you know what load needs to be connected so that the maximum power can be transferred. That's why the statement is telling you that Millmans theorem, Thevenin's theorem and maximum power transfer theorem are actually interlinked. Get that point? Now with the maximum power transfer theorem, you cannot bring in the Norton's network, because in Norton's network you have branches in parallel, the current would get divided, so you will not be having the maximum power delivered to the load. That's why it is the Thevenin's network we go with. Okay. Now let's summarize what we have seen all these days, okay, when we covered these theorems one by one. Okay. Now let's try understand the type of network that we need to choose for associating with the some of the theorems that we have looked at. See here, which network for Norton's? It is linear to it. If it is just linear, no, it is not sufficient. You need to have two terminals open, then only you can find out the Norton's equivalent, otherwise no. Okay, when there are no two open circuit terminals, you cannot ask find out the Norton's equivalent. If it is so, you need to ask across which two terminals. Understand that? The same thing happens with the Thevenin's. In Thevenin's also we deal with linear two terminal network. With maximum power transfer, what is that extra that we do? In maximum power transfer, you have linear two-terminal network, but across those two terminals, you are connecting the load, because we derive the conditions, right, for the maximum power transfer. Okay, so what load needs to be connected across those open circuit terminals for maximum power to be transferred? Okay, so that's why the type of the network or the circuit is two-terminal network with ZL or RL connected as load across these two terminals. So that is the network or the circuit that we consider if we have to deal with the maximum power transfer. In superposition, remember which type? It is linear. All the circuits that we are considering is linear, multiple independent source. Okay, if you don't have multiple independent source, superposition theorem is of no use. So that's why it's linear, multiple independent source circuit that you need to consider for superposition theorem. Okay, it's the dependent sources can be present, okay, but multiple independent sources have to be there for application of superposition theorem, because there we'll be seeing the contribution of individual sources when they are acting alone. Then we add them algebraically to get the total current or total voltage in the final step. Okay, so that is what superposition theorem is. In reciprocity, what type of network? See, linear, bilateral, single source. All are linear circuits. Bilateral, because here if we interchange, we have to think of interchanging the excitation and response positions. If you interchange the positions of the excitation and response, there should not be change in the response that we have. Fine. So such networks are called as bilateral, and for that reciprocity theorem to be applicable, you need to have only one source. Okay, if it is only one source, then you can think of reciprocity. You cannot deal with multiple excitations. No, you will obtain the response for one excitation. So that's why you need to be very particular when you are using the reciprocity theorem. You need to have just one source. Fine. Then Millmans, something that we have just seen, will have multiple generators connected in parallel. Multiple generators connected in parallel means you need to understand it will have its own EMF and the impedance which is internally connected. Understand? So if you have such parallel combination or the parallel connections of generators, we can apply Millmans theorem, which again is linear two-terminal network. See, all the networks that we are considering are common. How they are similar? They are all similar because we are considering all linear networks. Fine. So this is what we have seen all through when we were dealing with the theorems. Okay, and in the syllabus, the syllabus that in the module that I have covered is module 2, wherein you have all these theorems, 6 theorems. So all the 6 theorems we have dealt with. So it was actually for 10 hours, but here we were asked to cover this by 6 hours. So we have done that. More problems needs to be solved, which we were not able to because of the time constraint here. Okay, module 1 is already covered. Okay, now in the following sessions, in the following lectures on network analysis, all these modules are going to be covered. Fine. And regarding the textbooks, you have Van Valkenburg and Roy Choudhury as your prescribed textbooks, which deal with very good theory that supports the different techniques that we can apply to solve a problem or analyze a network or a circuit. Okay. Along with that, one more textbook that I would like to name is Network Analysis by K. Chenna Venkatesh and D. Ganesh Rao. Okay, so this is another book which makes interesting study. Okay, so this book has variety of problems solved. Okay, and it's not that we have to follow the same method which they have approached with. Okay, you just try getting the circuit, any of the textbooks. So all these textbooks, they are all good textbooks. Take circuits from there, and whatever you have learned so far, okay, in mesh analysis or node analysis, super mesh, super node, transformation, source shifting, whatever techniques you have learned, try applying on that. Okay, that would make your learning better and better. So with that, I would like to thank VTU EduSat program for giving me this opportunity to deliver this online lectures, and I'm also grateful to my management, National Education Society, and our principal of JNNCE, and our HOD, the lecturers, the colleagues, and also the students with whose support I'm here today. Okay, and if you have any queries to be asked, you can mail me at this email ID, that is mdsunil.dev@jnnc.ac.in. You mail me the queries, I'll reply to that. Fine, and hope you have understood and this lecture series was beneficial to you. Thank you. Thanks a lot. All the best. So time difference.